Hello, Dana. Hello. It's okay. I'm just as cooked as you are. I'm literally just starting the review right now. So, uh, let's see how far this goes. I'm probably gonna be reviewing like in math tomorrow. So. Empirical formulas. Honestly, just gonna like go through the whole thing. Uh, empirical formula. Molecular's the whole thing. Percent composition. Mass over mass times 100. Just percent composition is mass. Oh yeah, if there's any questions, just you can just send it in the chat or like DM me on Instagram. I'll see if I can answer them. Mole unit review. Atomic number and mass. Ooh, separation techniques. Gotta review that. Number of protons. Wait, chat. Do you guys know if like, do you know what like booklets we get? Like, do we need to memorize all the polyatomics and stuff, right? There's mechanical solutions. Solutions. Solubility charts has them? Oh, I guess some of them. Not all of them though. Okay, we don't get a pressure chart apparently. So yeah. Okay. Elements and compounds. Okay, so just more than one element basically. Separating mixtures. Hand separation, filtration, pour through a paper filter, dissolution, which are added to water, soluble and insoluble, crystallization, which are dissolved in hot water, solution cools down and crystals formed. More soluble are removed with the water and less solubles form crystals. Gravity. Okay, so we have you can use a highlighter. Okay. Needs hand separation, filtration, solvation / dissolution, crystallization, same thing except it takes a longer time. Gravity in a centrifuge. So the more denser ones would be separated. Centrifuge. Evaporation or distillation. So this one removes the volatile liquids and solids or non-volatile liquids. Okay. Wait, what's a volatile liquid? Evaporates readily at normal temperatures. Okay, that makes sense. Paper chromatography. Mixture is placed on a piece of paper. One side of the paper is submerged in water. So more soluble components move faster. Yeah. So paper chromatography. Okay. Atomic units, electron configuration. Electron configuration. Oh, right. Electron. What? When do we get it? Electron configurations. Okay. Energy levels. Quantum, the energy associated with the transition between two energy levels. Orbital, region of space occupied by an electron in a particular energy level. SPDF. So S shells, P shells, D shells, F shells. On the periodic table, should probably just get a periodic table. You can't see it at all. I can't see it. What? This is so blurry. This one looks okay. Okay. So it goes S shells, P shells, D shells, then F shells, right? I think 1, 3, 5, 7. Right, okay. Orbitals, shells, set of all orbitals have the same in value. So it goes orbital, subshells, orbital, shells. Oh, okay. So it goes shells. So that's like the whole energy level. Then the subshells, and then the orbitals. Always fills up in the order SPDF. Orbital diagrams. Yeah. Circular diagram of represents an orbital, each of which can hold 2 electrons. Rules when filling in orbital diagrams. An orbital may contain no more than 2 electrons. Electrons occupy the lowest energy available orbital first. Remember, order of energy. The first list orbital according to the distance that draw in diagonals. So S, 2S, 2P. So it goes this way. Yeah, okay. S shape always have one orbital. Up, down, up, down. Okay. Predict the electron configuration of the following using core notation. So AU, we're going to start. Okay, so for the ions, we can just write it. It's the same thing as the actual thing, pretty much. Yeah, so for full shells, we can write it both ways. AU xenon plus 2p oh, AU has that like special thing. Right. So where's the special columns again? Core notations for ions. Right, okay. Electron configuration of manganese is argon 4s2 3d5. Because the 4 electrons will be lost first. The 4s electrons will be lost first. All elements with 3d valence electrons tend to lose 2 4s electrons to form 2 plus ions. They are known as the 3d transition metals or transition metals. Okay, so these are all the transition metals. Yep. Scandium readily forms only Sc3 plus ions by losing this 3d. So scandium is here. Oh, so scandium can still lose its 3d ion by losing this 3d electron. By losing, and so it loses all 3, and due to having only one 3d electron. Such as the off-bow, Cu and Cr. So instead of expected configuration, it fills expected configuration, instead it steals one from the 4s squared. Same thing here, steals one from the 4s. Okay. So this column and this column are special because it wants to. Right, okay. Yep, so AU here, if we were to write AU would be xenon. That's 1, 2, 3, 4, 5 5s1 3f 14 and then 4d 10. Right, is that what I had? Oh, 6. Oh, I was off by 1. So 1, 2, 3, 4, 5, 6. Right, okay. Yeah, so 6. So 6s1, 3, 4f14, 5d10. Chat, who's ready for the test? Like, who's actually ready? Like, who isn't like just starting review tonight? Ions, they look fine. Matter and atoms test. Structure, chemistry. Atoms and electron configuration. Just take a look at this one. Core notation should be fine. Valence electrons. Right, so not found in the core or filled DF orbital shells. As a result, these ones get passed. Magnesium has the same and has 2 valence electrons, 3s2. Same token. Atoms from ions and orders give them configuration of a noble gas, right? Yep. So what about stuff in like the D shell? D shell electrons count as valence. Usually only the electrons of the higher energy level, but for transition metal after the count 2. Okay, so they are valence electrons as well. Okay. Period trends and period family. Tet rule. Yep. Period family notes. Periodic trends. Do you think we're gonna have to like remember all this? Increasing reactivity, low melting point, very reactive with water, react easily with air, soft but harder than less reactive, react with water. Much harder, higher melting points, good conductors. Non-metals, diatomic molecules, some are gases. Some are very reactive. Reactivity decreases. Right, because it's the most electronegative. Hydrogen, very reactive. Metalloids, semiconductors. Oxides of period 2 and 3 elements. Basic acidic or metal oxides are basic, non-metal oxides are acidic. Amphoteric oxides react both with acid and with basic. Okay, I don't think we need to know that. Acid rain when react with rainwater to produce an acidic solution with a low pH. Okay, so low pH is acidic, right? Periodic trends. A periodic table is organized by trends: ionization energy, metallic properties, atomic radii, electron affinity, electronegativity. To remove an electron from a natural gaseous atom. So it's easier as you over here and really hard for noble gases. Yep, so really easy for lithium but hard for the noble gases. Metallic properties. Conductor, the electricity, because they have free electrons. Shiny, malleable, and ductile. As you go across the periodic table, the number of E and P plus increase. There is more electrostatic attraction and smaller atoms. So it increases going across and increases going down. Oh, we know it decreases going across because there's more attraction. Okay. Of ions, so as fluorine picks up an electron, there's more electrons and therefore it's going to get sucked in close. Oh no, there's more electrons, so and then they're going to become larger because there's more repulsion between the electrons. As lithium loses an electron, it has a full outer shell and the repulsion decreases, therefore the ion becomes smaller. Okay, so with determining atomic radii, you have to look at the attraction between the protons and the electrons, but with ions, you need to look at the repulsion between the electrons. Electron affinity, energy released when an atom absorbs one electron to make a negative ion. Absorbs one electron. Electronegativity makes sense. Yeah. The energy released when an atom absorbs one electron to make a negative ion. More spontaneous, releasing the most energy. Stong said we have to? Oh, that's annoying. Oh well. Halogens are most likely to gain an electron, releasing the most energy. Okay. Periodic family. Writing and naming chemical formulas. Metal, nonmetal, metal, nonmetal, polyatomic. Okay, what are like the 10 prefixes? Mono, di, tri, wait, prefixes of covalent compounds. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay. Right, covalent compounds. Naming chemical formulas, multivalent compounds, polyatomic. Oh, it's right here. Okay. Yep. Periodicity. Okay. Balancing, I think we're fine. Oh, that's just a data table. Okay, that's good to have. Mole to mole stoichiometry worksheet. Mole mass stoichiometry. I think stoic is generally fine. Limiting reactants. Molecular bonding. Okay, gotta review the forces. What does VSEPR stand for? Valence shell electron something repulsion? Valence shell electron pair repulsion. Okay, so this is where we went through the different linears, 180, planar, trigonal planars, 120, tetrahedral, 109.5. Tetrahedral, 109.5. Then trigonal bipyramidal, trigonal bipyramidal. Trigonal linear is like this. Trigonal planar is like this. Tetrahedral is like this. Trigonal bipyramidal. Wait, is that all? I didn't think that was all. Hello. Welcome to the stream. Don't worry, I just started reviewing. I'm literally I started from the very beginning, so started from the very beginning of what we did this year. wait. SnCl2 would have SnCl2 because it would be like, and then right, tetrahedral. Oh, okay. So we don't need to know trigonal bipyramidal, but there's a few different cases for tetrahedral. So depends on how much centers there are. Oh, right. So I guess I'll move this then. So trigonal planar, if there are 0 lone pairs, then that's 120 degrees. But if there's one lone pair, then it'll look something like this, like SnCl2. And since this angle is going to be smaller than 120 degrees. For tetrahedron, or tetrahedral, lone pairs. So if there's 0 lone pairs, that would just be a normal tetrahedral, something like that. That would just be 109.5 degrees. Right? Then if there's 1, it would be something like that, or like that. Then 3 at the bottom. That would be it's going to be 107 degrees. And then if there's 2 lone pairs, so that's something like, and then it just has 2 of them, or there would be 2 pairs like that. So that would be like 104.5 degrees, and that's, for example, that's like H2O. Okay, 109.5, 107, 104.5. Okay. Oh yeah, apparently HCl is classified as tetrahedral, and it's classified as having 3 lone pairs because it's supposed to be like this. So that's the chlorine, and then that's the hydrogen. So apparently that's supposed to be a tetrahedral. Okay. Do we really have to memorize the angles? Apparently, yeah. So, yeah. Oh yeah. I can share this board with everyone. Yeah, I'm not kidding. HCl is considered tetrahedral. I'll show you guys a picture. See, HCl is considered tetrahedral for some reason. Apparently the chlorine has three lone pairs and one hydrogen bond. So it's so it's tetrahedral for some reason. I doubt it's gonna be on the test, but yeah, the delay is pretty hard. So yeah, I'll try to read the chat and type in chat. Chat is not so delayed. So, am I gonna eat the chem final, or is chem final gonna eat me? Don't worry, you'll cook it. We'll all cook on the final. Don't worry, chat. Okay, so bond angles should be good. By the way, everything is recorded, so if you need, to watch everything again, you can just go back. No worries. Intermolecular forces. Bonding. Wait, where's the intramolecular? Wait, okay, hold on. Intermolecular forces. What? Intermolecular forces. Yes, intramolecular forces. Intermolecular forces is those within the molecule that keep the bonds between the atoms. Intermolecular. Okay. Right. So. Intermolecular forces vs intramolecular forces. Okay. Apparently the final is the worst test of them all. You'll cook the final, the rest of us will just be I don't know. It's looking kind of grim for me too. It's okay. I got tonight. It's still bright outside. It's still kind of bright outside. It's still early. Even Zichin was complaining about it. Yeah. He was talking like he was saying how the test wasn't that, well, it wasn't like that difficult, but like he said there wasn't a lot of time. So you just gotta pick an answer and go. That's what I'm getting out of it. Intermolecular forces. Intra are those within the, so this is atom to atom, and this is molecule to molecule. So atom to atom, there's like metallic, there's covalent. Wait, I forgot what they're called. Covalent bonds non-metal bonds. Metal, non-metal. There's polyatomics. Molecule to molecule, there are London dispersion, dipole induced. Oh boy. Okay. Induced dipole. Dipole. And H bonds. Right. So ionic bonding, intermolecular bonding, intra happens between. Wait, what? That's what? Okay, intra happens between the atoms. Intra is like within. Inter is between the molecules. Okay. Oh yeah, ionic bonding. Yeah, ionic. I think Thong mentioned that there might be scaling depending on the. Yeah, apparently that's what Zichin was saying too. If Wan and Thong taught us things we couldn't be cooked, but right now I'm organic chemistry #1. Thanks. I hope I don't get cooked though. So yeah, apparently there might be scaling because if you think about it, 40 multiple choice questions is a lot. Like normally what we have on tests is like 10, and honestly those questions they take a long time. 40 questions for 75 minutes, and then plus another 10 response questions. I feel like chem is just practice. Ionic bonding, electrostatic attractions between charged atoms forming a lattice, sharing of at least one electron pair. Metallic bonding, the atoms in the middle have lots of delocalized, making the atoms positive and allowing the free-floating electrons to keep the atoms together. Types of intermolecular. Oh, they're called van der Waals forces. So, van der Waals. So there's London dispersion, dipole induced dipole, and hydrogen bond. London dispersion is just kind of when they like shake around and then they form like an accidental dipole. Yeah, so really weak. Relative strength. Yeah, very, very weak. Tighter hold. Electrons. Larger atoms will experience more London dispersion forces because they have larger atomic radius and they kind of like shake around. I'm just using formulas, but I don't actually know why. Oh. Even though electrons small, as molecules get bigger, there are enough London dispersion forces. Dipole-induced dipole. Dipole-induced dipole can also occur when a polar molecule's dipole causes a non-polar molecule to form a temporary dipole. The dipole of water induces a dipole in oxygen by distorting the O2 electron clouds. So with dipole-induced dipole, you need a dipole and a not dipole. So when you like put stuff in water, when you like dissolve stuff in water, even if the thing isn't like considered a dipole, it can still it can still have induced dipole reactions. Dipole, this one's pretty straightforward. Higher boiling point, higher melting point, more energy is required. The greater the intermolecular forces, more energy is required to change the substance, right? Ethane is nonpolar, has a molar mass and a boiling point of negative 161 degrees. HCl is polar and has a molar mass of 36.5 and a boiling point of 85. Yep, so hydrogen bonding, a special type of dipole. So hydrogen bond only works with H to N, H to O, H to F. Very electronegative. They suck in that hydrogen, making the hydrogen really positive, and then that makes a really strong dipole. Hydrogen will increase boiling point in relation to molar mass, increase viscosity, so higher boiling / melting points, increased viscosity, and increased surface tension. Surface tension. All right. I have to Google all the questions in the review because I don't understand the question to even answer it. Oh no, that's not great. I'll see if I'll go over some of the review questions in a bit. Gas laws notes. I'm gonna skip gas laws just because I'm a physics student and I don't really need it. So. Oh wait, there is actually one thing. The mole fraction thing. Partial pressure. Yeah, partial pressure. This one's actually important. So, partial pressures. So when you're adding stuff to like a container, even if you put more molecules in, volume, it's not going to change. So volume is constant. So if two or more gases are mixed, P total equals PA plus PB plus PC. And you can calculate each of these using PV equals nRT. Yeah, so since volume is constant, so P would be nR over V times T. Or RT over V times N. And since this is a constant when all the gas is in the same container, R is a constant, temperature is a constant since they're all in the same container, volume is constant since they're all in the same container, we have P is directly proportional to N. So therefore the ratio of the P's, so PA to PB to PC equals NA to NB to NC. Yep, that makes sense. The mole fractions. Wait, do you guys know if we get a pressure chart? I don't think we get the pressure charts, right? What the test is out of? 50? Yeah, 10 multiple choice and 10 written. 40 multiple choice. Yeah, Scantron. Will I do math today? I could go over some math at the end, sure. What do you want to go over though? Like just like if I were to go over, I'd probably just go over like calculator stuff. Wong said it was 10 marks for written, not 1 mark each. Multiple choices 1 mark each, yeah. Multiple choices 1 mark each. 10 marks for response questions. See, takes time though. Kidding. Right. Okay. Partial pressure, gas loss, enthalpy. Bond enthalpy. We get the enthalpy data table, right? We have to get the bond enthalpy data table. Measuring enthalpy changes, chemical energy. Yeah, definitely move on if you get stuck. It's gonna be so, yeah, pacing yourself's definitely gonna be hard. Periodic table and calculator, and a solubility chart. Actually, I don't think you get the solubility chart. I don't think you get it. We get solubility? Oh, okay. Okay. Chemical energy. See, I'm just gonna copy this over. Measuring enthalpy changes, chemical potential energy, heat, kinetic energy, temperature, system, the focus, which is the chemical reaction, open system, transfer of matter and energy is possible, closed system is not possible, though energy may be transferred. So closed system means heat can still go through. So heat, yes, but in an isolated system, heat cannot go through. Surroundings, the apparatus in which the reaction is taking place. endothermic and exothermic. So when you break a bond, let's draw it this way. When you break a bond, that's endothermic. So that requires energy. So delta H is positive. And when you're forming a bond, that is exothermic, and delta H is negative. That makes sense, because they're further apart, therefore they have more potential. And when they're closer, they have less potential, so they have to lose energy, basically. Yeah, that makes sense. Like, if you want to pull them apart, you need to give it energy to, to counter that potential energy. So delta H is positive. What's Hess law? I don't even remember this. Aaron said we got it? Okay, that's good. Oh, okay. Hess law is just like adding that stuff. Okay, this is just math, literally. So, calculate delta H from the following data. I do want to do a bond breaking kind of question, though. Let me see if there's one in here. Oh, and calorimetry. Also physics stuff, but I'll write it here. Q equals mc delta T. That's pretty much all you need to know. So when you're calculating the enthalpy of something, let's say you have like, I don't know. Let me see if they had an example. Let's just say I had like something like NaOH plus HCl gives like NaCl plus H2O. So first of all, if you want to calculate enthalpy, you need to like break all the bonds. So bond breaking. Now this step is actually delta H is negative. So make sure like whatever your calculations that you come up with, you take the negative one. And on this side, it's bond forming, and that requires energy. So this is when delta H is greater than 0. I guess a good way to remember like the H is positive or negative is like as the stuff forms, if there's more stuff on the left side and less stuff on the right side, you can just think of like some. So let's say you had like elements A or B gives like element C, then delta H, like if it forms something, that means basically it's this side's like missing something, right? There's two things on the left side, one thing on the right side. Right side's missing something, so delta H should be greater than 0 to compensate for that like loss of something. I don't know, just like a way to remember it, I guess. Okay, Hess law, reactivity. Why do I not remember this? Oh, calculating enthalpy changes. Standard enthalpy change. Density of water, specific heat capacity. Oh, so standard enthalpy is then you have to convert it to per mole. So enthalpy is energy per mole. Yep. Okay. Ion concentrations and dilutions. Oh, we're finally reaching the end. Okay. So this is the net ionic equation stuff. That's just a solution. Okay, well, net ionic equations, we just learned it, so I think you should be fine. So I won't go over that. Final review package. Okay, chat. Should I go over the review package, or I'll do a few questions in it. Okay, I'll just go over some of these then. This is fine. Isotope. Oh yeah, what are isotope? Oh, so isotope is when it has like an extra neutron, but ion is when it has an electron. different number of neutrons that have gained or lost. Okay. So which one is a magnesium isotope? It's B. So which ion could it be? Okay. Lewis structure. What is the shape of the SO2 molecule? This should be triangular planar. Yeah, which molecule? Wait, no. Bent? Wait, what is bent? Hold on. Oh, so it's supposed to be bent. Oh, I guess. Yeah, okay, that makes sense. So bent is just triangular planar, but with with only two centers. Which molecule is polar? Should be this one. Wait, PCO. Yeah, it should be A, yeah. Which compound forms hydrogen bonds in the liquid state? Hydrogen bonds. Should be C. A? Oh, okay, yeah, that makes sense. OH, yeah. How do the bond angles in CH4? So CH4 is 109.5. NH3 is smaller. H2O is even smaller, so it should be D. Yeah. Which is the best description of the ionic bonding? Electrostatic retraction between oppositely charged ions. Yep. Correct Lewis word for hypochlorous acid, a compound of chlorine, hydrogen, and oxygen. Can't be A or B. Should be D, I think. No. Yeah, it's C. Okay. Trying to increase this down group 1. Reactivity. Generally decreases across period 3. Atomic radius decreases, right? Yeah. Which ion has the largest radius? Chlorine minus. Should be bromine minus. So C. Yeah. Group 4 and period 3 of how many electrons are the highest occupied energy of this element? Period 3. So it should just be group 4. Oh, so it should just be 4 then. Yeah. Why the relative atomic mass of argon is greater than the relative atomic mass of potassium, even though the atomic number of potassium is greater than the atomic. Because potassium is bigger than argon. Deduce the number of protons and electrons. Okay, this is pretty simple stuff. Silicon has 3 symbols. Okay, relative. Calculate the abundances. Okay. Yeah, I realized after. But yeah, thanks for the note. Draw the Lewis structures. Ethane hydrides of adjacent elements. Draw Lewis Shaw. Yep. Mole stoichiometry. I'm gonna skip this part. Solution stoichiometry. I'm gonna skip this part too. Stoichiometry in general isn't that bad. Gas stoichiometry, volume, can be formed by the reaction between 2 and H2. Equations. Can be produced from the complete decomposition of mercuric oxide. Oh, right, so some stuff to know. Guess I'll write it in the pressure section. Molar, what is it called? So gases take 22.7 liters per mole. Or is it 22.4? Okay, yeah, so it's 22.4, not 22.7. Right, so that's definitely something to know. And I guess like 1 ATM equals 10 to the 5 pascals, which is also ATM to torr. 760, right? 760 torr equal to 760 millimeters of mercury, which is Hg, right? Should be 22.4. Yeah, so 22.4. Yeah. Wait, so when is it 22.7? It's always, no, it's 22.4. It's 22.4. So before the standard pressure was 1.013 times 10 to the 5 Pascal. And then after it changed to 1 times 10 to the 5, it became 22.4. It was 22.7 before, yeah. So yeah, use 22.4. Okay, I asked when we did gases in when we did PV equals nRT in physics, I asked Miss Greenwood, and she said standard pressure is like 1.013 times 10 to the 5. Like, I think physics accepts 1.013 times 10 to the 5, but Mr. Wan said it's all, like, after they changed it, we always use just 1 times 10 to the 5. So, yeah, just something, I guess. Thermochemistry, yeah. This, just remember, like, bond breaking is negative and bond forming is the positive one. But thermochemistry is it's literally just math, just solving equations. So. Wait, it should be 22.4, right? Hold on. Is it 22.4 or 22.7? Oh, yeah, okay. If you use the old values, it's 22.4. Oh, so the new one is 22.7. He wants us... So Mr. Wan wants us to use 22.7, right? Molar volume with new pressure. Yeah, okay, so use 22.7. Never mind what I said before. So 22.7, right. Right, because they decrease the pressure, so then there's more room for the gas, so it would increase the volume. Yeah, that makes sense. That makes sense. Chat, is this real? Yeah, it's supposed to be 22.7. It used to be 22.4. Oh, my bad, guys. My bad, chat. My fault. I'm just kidding, guys. I'm actually here to throw you guys off so that the curve is easier for myself. That's why you should keep watching. I'll feed you all the wrong information, and then you'll do bad on the test. Exactly. It's all part of my plan, guys. Alright, alright, alright. Okay, okay. I think that's it for the review. Right. Okay. Alright, chat. You guys got any questions? If you guys have any questions, you can send them to me. But it's getting pretty late, so should rest for the test tomorrow. Yeah, no problem, guys. Just don't report it to IB, okay? Oh yeah, HL students, show up tomorrow 8 p.m. I'll be going over the unit 1 and 2 of Math HL. I'll see if I can get through some of unit 3. But 8 p.m. tomorrow. Right, okay. I'll send this link. Send this link again so you guys can see the notes. My notes are pretty ugly, so probably have better. But just in case you guys want it. Yeah. But yeah, that's pretty much it. Go sleep, everyone. Go sleep. It's getting late. Alright. I'll end the stream at 10:30, so if you guys have any questions, send it in. Okay. Okay, I'll go over binomials real quick. Yeah. My notes are pretty ugly, so try your best. Try your best to read them. Hello. I can't see your names, so I don't know who you guys are, but okay, I'll do one section on binomials. So, Elisa, do you want the binomial theorem or like the distribution? Theorem, right? Like the expanding and stuff. Yeah, Lisa, if you don't respond in the next 2 minutes, I'm logging off. Alright, I'm logging off. Thanks for joining the stream, everyone. Remember, 8 p.m. tomorrow, HL stream review. So make sure to join up. Alright, I'm logging up. Thanks for coming, guys.